Hello and welcome to the Sleepy Science. I'm so glad you're here. Today we discuss that. Dreams and the sleeping brain, what science knows so far. As your eyelids grow heavy, the waking world softly blurs. Neurons begin their nocturnal dance, and consciousness slips into the gentle arms of sleep. What alchemy transforms alertness into dreams? The room around you grows softer, as if the air itself has thickened with twilight. Your eyelids, once fluttering like moth wings against light, now lower as though pulled by invisible threads. The book in your hands, its words now swimming like minnows in a slow current, will wait until morning. This is the threshold, that delicate borderland between wakefulness and sleep, where thoughts dissolve like sugar in warm tea and the body surrenders to gravity. You are not so much falling asleep as being gathered by it. Deep in your brain, a tiny cluster of cells no larger than a grain of rice begins its nightly ritual. This is your suprachiasmatic nucleus, the master clock that has kept time with the sun since your first breath. As daylight fades, it whispers to your pineal gland, which stirs like a night-blooming flower, releasing melatonin into your bloodstream. This is the hormone of darkness, the chemical lullaby that drifts through your veins, softening the edges of your mind. Meanwhile, your neurons are changing their rhythm. All day, they've fired in the rapid, asynchronous patterns of wakefulness, like a bustling marketplace full of individual conversations. Now, they begin to synchronize, their electrical pulses slowing and swelling into unified waves. First come the alpha waves, the gentle ripples of a mind at rest, like sunlight dappling the floor of a quiet forest. Then, as sleep pulls you deeper, theta waves emerge, the slower, more rhythmic pulses of a brain wading into unconsciousness. You might even experience hypnagogia, those fleeting, dreamlike images that flutter at the edges of consciousness as you cross over, a face. A face forming in the grain of wood, a voice calling your name in empty air, the sensation of falling that jolts you briefly awake. Your body is performing its own quiet symphony of surrender. Muscles relax as neurotransmitters like GABA flood your system, turning off the motor signals that keep you upright during the day. Your breathing slows and deepens, your heart rate settles into its nocturnal rhythm, and your core temperature drops by nearly a degree, a biological echo of the Earth's cooling at night. Even your gut joins this chorus, as digestive processes slow and the microbiome, that universe of bacteria inside you, shifts its activity to nighttime mode. The most mysterious transformation happens in your consciousness itself. As the thalamus, the brain's sensory gatekeeper, begins to dampen its signals, the outside world grows distant. Sounds seem to come from farther away, touch feels muted, and your sense of time begins to stretch and warp. This is the brain's sensory curtain drawing closed, separating you from the waking world. Yet paradoxically, as external input fades, your internal world grows richer. The default mode network, the web of brain regions responsible for self-reflection and imagination, becomes more active, setting the stage for the dreams to come. All through this descent, your brain is making careful calculations. Sleep pressure, built up by the accumulation of adenosine molecules throughout your waking hours, must be balanced against your circadian rhythm. A tiny structure called the ventrolateral preoptic nucleus acts as a sleep switch, inhibiting the arousal centers that keep you awake. It's a delicate equilibrium, this transition from light to dark, from activity to rest, one that your body has perfected over millions of years of evolution. As you hover in this liminal space, neither fully awake nor truly asleep, you might notice how thoughts become untethered from logic. Words blend into images, memories rearrange themselves freely, and the boundaries between self and world grow porous. This is the mind preparing for dreams, loosening its grip on reality's rules. The sensation is not unlike floating in warm water, supported, weightless, drifting where the currents take you. Tonight, as every night, this transition is both ordinary and extraordinary. The same biological processes that guide you into sleep also guided your ancestors, back through centuries of human history, back to the earliest mammals who hid from predators in the dark. The machinery is ancient, yet it renews itself in you each evening, this daily rehearsal of small death and rebirth. And now, as your breathing deepens and your muscles go slack, as the last conscious thoughts dissolve like ink in water, you might wonder, what awaits in the deeper waters of sleep, where the brain's waves grow longer and more mysterious. That journey begins in the next tide of night. The tides of your sleeping brain. Sleep is not a still pond, but a sea with waves, each phase rolling in, then receding. From the shallows of light sleep to the depths of delta waves, your mind embarks on a rhythmic voyage. As you drift beyond the threshold of slumber, your brain begins its nightly pilgrimage through layered landscapes of consciousness. This is not a single state, but a cycling journey, one that repeats every 90 minutes like the turning of a celestial wheel. Imagine your mind as an ocean, with waves of electrical activity rising and falling in perfect, moon-pulled rhythms, each phase washing over you with its own unique texture and depth. The first waves to arrive are gentle, the light lapping of stage 1 sleep. Here in these shallows, your brain produces theta waves, slow and rolling like the drowsy currents of a sun-warmed river. Your muscles relax completely now, as if the strings holding up a marionette have been loosened. In this fragile borderland, you might twitch suddenly, a phenomenon called a hypnic jerk, perhaps an evolutionary remnant from when our ancestors slept in trees. Your breath grows even, your heart finds its slower night rhythm, and your eyes, beneath their lids, make slow, rolling movements as though watching some invisible tide come in. Deeper now, into stage 2, where the brain begins spinning sleep spindles, brief bursts of activity that dance across your neural networks like fireflies in a summer field. These spindles, generated by the thalamus, are thought to be the mind's way of protecting sleep, creating a barrier against outside disturbances. Your body temperature drops further, your breathing becomes more regular, and your brain begins the important work of memory consolidation, sorting through the day's experiences, deciding what to keep and what to let fade. Scientists believe these spindles may be why we often sleep better in our own beds, the familiar surroundings allowing the brain to spin its protective cocoon more efficiently. Then comes the descent into slow-wave sleep, stages 3 and 4, where the brain's waves lengthen into deep, resonant delta patterns. These are the tides of restoration, when growth hormone floods your system, repairing tissues and strengthening your immune defenses. Your blood pressure drops, your breathing becomes so shallow it might worry a waking observer, and your brain begins clearing metabolic waste through the newly discovered lymphatic system, a process more efficient during these delta-laden hours than at any other time. This is when the body truly renews itself. Children spend nearly 40% of their sleep in these deep stages, while adults gradually lose this capacity over decades. After nearly an hour of this deepening journey, something remarkable occurs, the tide turns, and you begin ascending back toward consciousness. But instead of waking, you enter the most mysterious phase of all, REM sleep. Your brain's activity spikes to near-waking levels, your eyes dart rapidly beneath closed lids, hence rapid eye movement, and your muscles enter a state of temporary paralysis, nature's way of preventing you from acting out your dreams. Your breathing becomes irregular, your heart rate increases, and in males, blood flows to erectile tissue, all part of the autonomic nervous system's activation. This is when the most vivid dreams occur, when your mind weaves stories from the threads of memory, emotion, and imagination. The entire cycle, from light sleep through deep sleep to REM, repeats 4 to 6 times each night, each iteration slightly different from the last. Early in the night, the deep wave stages dominate. As morning approaches, REM periods grow longer while deep sleep becomes shorter. This pattern is so consistent that sleep researchers can estimate what time you went to bed simply by examining your brainwave patterns. Your brain's geography changes dramatically during these cycles. The prefrontal cortex, the seat of rational thought, goes quiet, while emotional centers like the amygdala remain active. The visual cortex lights up during REM, even though your eyes are closed, while the motor cortex fires as if you were running or dancing, though thanks to that muscle paralysis, your body stays perfectly still. The default mode network, active when we daydream, becomes the dominant player, explaining why dreams often feel so immersive yet illogical. These cycling stages appear to serve different but equally vital functions. Deep sleep is when the brain clears out toxic proteins like beta amyloid, associated with Alzheimer's disease. REM sleep seems crucial for emotional regulation. People deprived of REM show increased emotional reactivity the next day. Both stages contribute to memory consolidation, though in different ways. Procedural memories, like riding a bike, benefit from deep sleep, while emotional memories are processed during REM. As you ride these neural tides tonight, consider how each phase contributes to your waking life. That difficult problem you couldn't solve yesterday? Your brain will work on it during the new skill you practiced. Deep sleep will strengthen those neural pathways. Even your immune system learns during sleep. Studies show that vaccination responses improve when people sleep well afterward. The composition of your sleep changes across your lifespan. Infants spend nearly 50% of their sleep in REM, perhaps necessary for their rapidly developing brains. Young adults enjoy abundant deep sleep, while older adults experience more fragmented sleep with less delta activity. Women's sleep patterns fluctuate with menstrual cycles and pregnancy, while men show more gradual age-related changes. Yet regardless of age, the fundamental architecture remains. The cycling between light, deep, and REM sleep is a universal human experience, as fundamental as breathing. Tonight, as you float through these changing states, you might wonder, what happens when the brain's careful choreography of sleep stages is disrupted? What secrets might our dreams reveal about these nightly voyages through different realms of consciousness? The answers await in the theater of your dreaming mind. The theater of dreams. Behind closed lids, a stage lights up. Strange stories unfold, familiar faces twist, and gravity loses its hold. How does your brain craft these nightly plays, and why do you star in every one? As you enter REM sleep, the theater of your mind raises its velvet curtain. The stage is set not with props and backdrops, but with the raw materials of memory, emotion, and sensory fragments, all waiting to be woven into tonight's performance. Here in this private cinema, you are both audience and actor, playwright and critic, watching stories unfold that somehow feel intimately yours even when they defy all logic. The production begins subtly. At first, the scenes may resemble ordinary life. You're back in your childhood home, or having coffee with a friend. But then the dream logic takes hold, the walls breathe, time loops backward, or suddenly you're flying over cityscapes that morph like liquid. These transitions feel perfectly natural in the moment because your prefrontal cortex, the brain's reality checker, is offline. Meanwhile, your visual cortex blazes with activity, constructing vivid imagery from neural noise. Your motor cortex fires as if you're running or dancing, though your body lies still, protected by sleep paralysis. The amygdala, your emotional center, adds intensity to every scene, which explains why dreams often carry such visceral fear, joy, or wonder. Scientists believe dreams serve multiple purposes. One theory suggests they're a kind of overnight therapy, your brain processing emotional experiences in a safe space, stripping away painful associations while preserving important lessons. Another posits that dreams help with memory consolidation, as your mind replays and reorganizes the day's events. The threat simulation theory proposes that dreams allow us to practice responding to dangers, a leftover from our evolutionary past when survival depended on quick reactions. Whatever their purpose, dreams follow certain patterns. You're usually the protagonist, settings blend familiar places with impossible architecture, and time behaves like putty, stretching, compressing, or folding back on itself. The content of dreams reveals fascinating quirks of the sleeping mind. Despite living in a visually rich world, about 30% of dreams contain no color at all. People blind from birth dream in sounds, textures, and emotions rather than images. Common themes recur across cultures: being chased, falling, flying, or arriving unprepared for an exam. These universal motifs may reflect shared human anxieties or fundamental ways our brains organize experience. Your dreams also incorporate real sensations. A blanket's weight might become a monster's grip, or a ringing alarm could transform into dreamworld sirens. Lucid dreaming, when you become aware you're dreaming, offers a glimpse into the brain's extraordinary flexibility. During these rare moments, The prefrontal cortex partially reactivates, allowing critical thought while the dream continues. Skilled lucid dreamers can sometimes control the narrative, flying by will or summoning dream characters. Neuroscience studies show these experiences involve a hybrid state of consciousness, parts of the brain awake while others remain in REM sleep. Some cultures have cultivated lucid dreaming for centuries, viewing it as a spiritual practice or creative tool. Your brain is remarkably active during these nighttime performances. PET scans reveal that during REM sleep, your visual and emotional centers light up while your logical prefrontal cortex remains quiet, the perfect recipe for vivid, emotionally charged stories that feel real despite their absurdity. The pons, a structure at your brainstem's base, sends signals that paralyze your limbs, preventing you from acting out dreams, while also generating the eye movements that give REM sleep its name. Meanwhile, your memory systems undergo temporary reorganization, which explains why dreams often slip away like morning mist unless captured immediately upon waking. Dreams follow their own mysterious chronology. A long, elaborate dream might represent just seconds of neural activity, your brain compressing experience like a master storyteller. Time dilation in dreams can make minutes feel like hours, or collapse vast stretches into instant transitions. Some researchers believe this flexible timescale helps the brain simulate different scenarios efficiently, running through possibilities much faster than waking cognition allows. The characters in your dreams, whether familiar faces or complete strangers, are all creations of your mind. Neuroscientists suggest your brain maintains a people database it draws from during dreams, sometimes combining features from different individuals into composite characters. Even when you dream of someone you know well, it's not truly them but your memory and perception of them, which explains why. Why dream versions sometimes behave unlike their real counterparts. As morning approaches, your REM periods grow longer, your dreams more vivid and story-like. This may be why you're more likely to remember dreams from the final hours of sleep. Upon waking, the fragile dream memories compete with incoming sensory information, unless you consciously preserve them. By lying still and replaying them, they'll evaporate within minutes. Some cultures keep dream journals, others share morning dream telling as a daily ritual. These practices recognize dreams as meaningful, whether as psychological reflections, creative inspiration, or messages from the subconscious. Tonight, as you drift into REM, consider that your dreaming mind is doing essential work, sorting memories, processing emotions, and perhaps even problem-solving. Many artists and scientists credit dreams with breakthrough ideas. Paul McCartney composed "Yesterday" in a dream, Dmitri Mendeleev envisioned the periodic table's arrangement during sleep, and Mary Shelley conceived Frankenstein's monster from a nightmare. Your ordinary dreams may not produce masterpieces, but they're still part of your mind's way of making sense of your waking life. As the final dream of the night fades and dawn light filters through your eyelids, you might wonder, where do these nightly stories go when forgotten? Are they truly lost, or merely folded back into the mind's raw materials, waiting to be reshaped into tomorrow night's performances? And what of the memories you do retain? How does your sleeping brain decide which experiences from today deserve preservation, and which should fade like footprints in sand? That quiet sorting begins in the archives of your sleeping mind. The architects of memory. While you sleep, librarians quietly organize the day's shelves. Fragments of conversations, forgotten details, and skills you practiced are woven into the tapestry of your mind. As you drift deeper into sleep's embrace, your brain begins its most delicate work of the night, the careful curation of memory. Imagine a vast library where each new experience is a book tossed haphazardly onto reading tables. Now watch as invisible hands emerge, some gently placing volumes into proper shelves, others binding loose pages into coherent narratives, a few even discarding irrelevant scraps into recycling bins. This is the hidden labor of your sleeping mind, transforming the raw material of daily experience into lasting memory. The process begins in your hippocampus, that seahorse-shaped region nestled deep in your temporal lobe. All day it has been diligently recording your experiences, creating temporary neural patterns that capture everything from the taste of morning coffee to the emotional weight of a difficult conversation. But these are fragile traces, like ink that hasn't yet dried on parchment. Without sleep's intervention, most would fade by morning. As you cycle through sleep stages, something remarkable occurs. Your hippocampus replays the day's events, but at nearly 20 times the speed of waking experience. Scientists first discovered this phenomenon by monitoring rats' brain activity as they navigated mazes, then observing identical neural patterns repeating during sleep. In humans, this replay happens most intensely during slow-wave sleep, when those deep delta waves wash through your brain like tides smoothing sand. But memory consolidation isn't mere repetition, it's active reorganization. Your brain performs three crucial tasks. Selection, like an archivist deciding which documents to preserve, your brain tags certain memories for strengthening based on emotional significance, repetition, or future relevance. That embarrassing moment at work? It might get flagged for retention because strong emotions act as memory markers. Integration, new knowledge becomes woven into existing neural networks. The French vocabulary you studied finds connections to words you already know, the piano melody you. As you surrender to sleep, your brain begins its sacred work of memory alchemy. Like a master archivist under moonlit skies, it sorts the day's fragmented experiences, some sealed in gold-leafed neural code, others gently dissolved into oblivion. The hippocampus, that seahorse-shaped scribe, transcribes fresh memories onto cortical parchment during deep slow-wave slumbers, while REM sleep's vibrant theater rehearses muscle movements until your fingers remember what your mind forgets. Painful memories lose their venom here, their emotional barbs carefully extracted by nocturnal healers. Beneath the surface, the glymphatic tide swells with celestial precision, cleansing neural shores of the day's metabolic debris. Children's brains spark like fireworks in this nocturnal workshop, constructing whole cities of new understanding before dawn, while adults reinforce existing pathways, their synaptic bridges growing stronger with each sleep cycle's careful tending. This is the hidden symphony of the sleeping mind, every night, a quiet revolution of reorganization, where yesterday's chaos becomes tomorrow's wisdom. That difficult problem at work? Sleeping on it genuinely helps. The brain continues working on challenges during sleep, often delivering solutions upon waking. Students who sleep after studying retain information better than those who pull all-nighters. Musicians who practice a new melody show improved performance after sleep, not just time passing. Even athletes benefit. Sleep enhances motor memory consolidation, making practice more effective when followed by rest. But memory processing during sleep isn't flawless. The system prioritizes emotional and survival-relevant information, which explains why you might forget a colleague's name but remember where you saw a spider. False memories can form when sleep-deprived brains misfile information. And with age, reduced slow-wave sleep correlates with memory decline, suggesting that improving sleep quality might preserve cognitive function. Your sleeping brain also engages in creative recombination, taking elements from different memories and combining them in novel ways. This explains dream strangeness, why your childhood home might appear in your current workplace, but also facilitates creative problem solving. The chemist Kekulé famously discovered benzene's ring structure after dreaming of a snake biting its tail, a breakthrough emerging from his sleeping mind's ability to rearrange existing knowledge. As dawn approaches and REM sleep dominates, your brain begins another crucial task: emotional memory processing. The same events replay, but now with reduced amygdala activity and increased prefrontal cortex involvement, essentially maintaining the memory while dulling its painful edges. This nocturnal therapy helps explain why sleeping on it often brings emotional clarity to daytime troubles. Tonight, as your brain cycles through these memory-enhancing stages, consider all it's working to preserve: the melody you hummed absent-mindedly, the feel of a loved one's hand in yours, the solution to a problem that eluded you at dusk. Each will be evaluated, connected, and, if deemed worthy, given permanent residence in your mind's vast archives. But what determines which memories fade and which remain? Why do some experiences from decades ago feel freshly minted, while yesterday's lunch disappears without a trace? The answers lie in the delicate chemistry of remembering and forgetting, a balance your brain maintains even as you dream. The language of REM. Rapid eyes dart beneath lids, muscles go still, and the brain blazes with activity almost like waking. This paradoxical state is where dreams grow vivid, and where mysteries whisper loudest. As you enter the REM phase of sleep, your body enters a state of beautiful contradictions. Your breathing becomes irregular, quick bursts followed by pauses as if you're running in your dreams. Your heart rate fluctuates wildly, responding to unseen dream events. Most remarkably, your eyes begin their characteristic rapid movements, darting back and forth beneath closed lids as though following some invisible tennis match of the mind. These physical signs hint at the extraordinary neural drama unfolding within. Your brain during REM sleep is a study in paradox. EEG readings show activity nearly identical to wakefulness. The prefrontal cortex, your rational mind, remains quiet while the visual, emotional, and memory centers blaze with intensity. This unique combination creates the perfect conditions for dreaming, vivid sensory experiences, strong emotions, and loose connections between ideas, all accepted without critical analysis. Blood flow to the brain increases by 20% compared to non-REM sleep, with particular activation in the limbic system, the seat of emotion and memory. Meanwhile, your body lies completely still, immobilized by a powerful neural mechanism that prevents you from acting out your dreams. The purpose of REM sleep remains one of neuroscience's most fascinating puzzles. Some researchers believe it serves as overnight therapy, your brain processing emotional experiences in a safe environment. Others propose it's crucial for memory consolidation, particularly for procedural skills like riding a bike or playing piano. The activation synthesis theory suggests dreams are simply the brain's attempt to make sense of random neural firing during sleep. More recently, the defensive inactivity theory posits that REM's paralysis may have evolved to keep vulnerable animals still and silent when predators are nearby. Your REM cycles grow longer as the night progresses. The first REM period might last only 10 minutes, while the final one before waking can extend to nearly an hour. This explains why you're more likely to remember dreams from early morning hours. During these later REM phases, your dreams become more complex and story-like, weaving together fragments of recent experiences with older memories in increasingly creative ways. The physiology of REM is exquisitely orchestrated. In your brainstem, the pons sends signals that trigger eye movements while simultaneously inhibiting motor neurons, causing the characteristic paralysis known as REM atonia. This paralysis is so complete that even your middle ear muscles, which normally respond to loud noises, become inactive. Yet some systems remain strangely active. Your genitalia show increased blood flow unrelated to sexual dreams, and your thermoregulation shuts down completely, which is why you can't maintain REM sleep when too cold or hot. REM deprivation studies reveal surprising consequences. When prevented from entering REM either experimentally or through certain antidepressants, people experience rebound REM, their brains desperately making up for lost time by entering REM faster and staying longer on subsequent nights. Chronic REM deprivation can lead to emotional instability, difficulty concentrating, and even hallucinations, suggesting this sleep phase plays crucial roles in mood regulation and cognitive function. Across the animal kingdom, REM sleep appears in mammals and birds, with some fascinating variations. Dolphins and other marine mammals sleep with one brain hemisphere at a time, to maintain breathing at the surface, and show REM characteristics in the awake hemisphere. Platypuses, those strange egg-laying mammals, experience an extraordinary 6 to 8 hours of REM per day, possibly related to their complex sensory systems. Even chickens demonstrate REM-like states, complete with rapid eye movements beneath closed lids. Your REM sleep changes throughout your lifespan. Newborns spend about 50% of their sleep in REM, likely supporting their rapidly developing brains. By adulthood, this decreases to 20 to 25%, with further reduction in older age. Some researchers believe the abundance of REM in early life helps with neural pruning, the essential process of strengthening important connections while eliminating less used ones. The content of REM dreams follows certain patterns. They're more likely to involve aggression than non-REM dreams. You're often running from threats rather than facing them calmly. Flying dreams typically occur during REM, as do those with impossible physical transformations. Interestingly, while REM dreams feel longer, time perception in dreams correlates fairly well with real time. A 5-minute dream typically reflects about 5 minutes of neural activity. As morning light filters through your eyelids and your final REM period of the night concludes, your brain begins its gradual return to waking consciousness. The paralysis lifts in careful stages. First your fingers might twitch, then your limbs regain movement. Your breathing steadies, your heart rate normalizes, and your eyes, after their night of rapid movement, finally open to greet the new day. Yet the mysteries of REM linger like the fading traces of a vivid dream. Why did evolution create this strange state of active brain and paralyzed body? What purpose do those rapid eye movements truly serve? And how does this nightly theater of the mind shape who you are when awake? The answers may lie not in the stars, but in the quiet chemistry of your sleeping brain, the delicate balance of neurotransmitters that guide you each night from wakefulness to dreams and back again. The healing dark. Sleep is the body's silent repair shop. Cells mend, toxins flush, and the immune system takes its nightly inventory. Even your heart slows to a deeper, older rhythm. As you surrender to sleep's embrace, your body begins its most profound work of restoration. This is no passive state of inactivity, but an orchestrated symphony of biological renewal that has evolved over millions of years. While your conscious mind drifts through dreamscapes, every system within you engages in meticulous self-repair, processes that can only occur when the demands of wakefulness are set aside. Your cardiovascular system is first to sigh with relief. As you transition through sleep stages, your heart rate gradually decreases by 15 to 30 beats per minute, and blood pressure drops by 10 to 20%. This nightly respite is so crucial that chronic sleep deprivation can lead to sustained hypertension, your cardiovascular system never getting the break it requires. The rhythm of your heartbeat changes too, becoming more variable in deep sleep, a sign of healthy autonomic nervous system function. Research suggests these nocturnal changes may explain why people who consistently sleep less than 6 hours nightly face significantly higher risks of heart disease and stroke. Meanwhile, your endocrine system recalibrates its delicate balance. Growth hormone, essential for tissue repair and muscle growth, is released primarily during slow-wave sleep, with children secreting up to 5 times more than adults during these restorative phases. Your pancreas adjusts insulin production to maintain stable blood sugar levels, while leptin and ghrelin, the hormones regulating hunger, rebalance themselves. This hormonal reshuffling explains why sleep deprivation often leads to increased appetite and cravings for high-calorie foods the following day. At the cellular level, the night shift is bustling with activity. Damaged proteins are cleared from muscle fibers, mitochondria, the power plants of your cells, undergo maintenance, and stem cells proliferate to repair minor injuries. Your skin cells increase production while UV-induced damage is repaired, giving literal truth to the term beauty sleep. Even your hair follicles follow circadian rhythms, with peak growth occurring during rest. The immune system conducts its most vigorous work during these quiet hours. Cytokines, proteins that regulate immune responses, are released in greater quantities during sleep, helping coordinate defenses against infection. Studies show that people who sleep less than 7 hours are nearly 3 times more likely to develop colds when exposed to viruses. Your lymphatic system becomes particularly active during sleep, flushing waste products from brain tissue through the newly discovered lymphatic system, a process that may help prevent neurodegenerative diseases by clearing beta-amyloid proteins associated with Alzheimer's. Your brain's self-maintenance is perhaps the most extraordinary of all. During deep sleep, the space between brain cells expands by about 60%, allowing cerebrospinal fluid to wash through neural tissue like a gentle tide, carrying away metabolic waste that accumulated during waking hours. This nightly brainwash may be crucial for preventing neurodegenerative diseases. When disrupted, toxic proteins can build up, potentially explaining links between poor sleep and conditions like Parkinson's and dementia. Even your gut microbiome follows circadian rhythms, with certain bacterial populations becoming more active during sleep. These microscopic symbionts help regulate everything from digestion to immune function, and their cyclical behaviors suggest coevolution with our sleep-wake patterns. The gut-brain axis operates differently during sleep too, with communication along the vagus nerve changing character as you cycle through sleep stages. Children's bodies reveal sleep's restorative power in its purest form. During deep sleep, their pituitary glands release pulses of growth hormone so potent that actual physical growth occurs predominantly at night. The synaptic pruning that shapes developing brains, strengthening important neural connections while eliminating less used ones, occurs most vigorously during these early years' abundant slow-wave sleep. Even the immune system's memory of pathogens is consolidated during childhood sleep, helping build lifelong defenses. The consequences of sleep deprivation reveal how crucial these nightly repairs truly are. After just 24 hours without sleep, your body begins breaking down muscle tissue for energy. Within 3 days, your cognitive function deteriorates to levels resembling intoxication. Chronic sleep loss is associated with increased inflammation, impaired glucose metabolism, and even changes in gene expression, with studies showing that a single week of sleeping 6 hours or less per night alters the activity of over 700 genes. Yet your body demonstrates remarkable resilience when given proper rest. Most sleep deprivation effects reverse after 1 or 2 nights of quality sleep, though some damage, particularly to cognitive function, may require longer recovery. The phenomenon of sleep rebound, spending extra time in deep sleep stages after deprivation, shows your body's innate wisdom in prioritizing its most critical repairs. As you lie in bed tonight, consider the ancient wisdom of this daily restoration. The same processes occurring within you, cardiovascular rest, cellular repair, immune reinforcement optimizing mammalian biology for over 60 million years. Your body knows precisely how much slow-wave sleep your muscles need, how much REM your emotional balance requires, when to release which hormones in what quantity. This nightly healing requires no conscious effort on your part, only your surrender to the quiet dark. Your cells remember rhythms older than electricity, older than civilization, older than language itself. The wisdom written in your DNA still follows the primordial patterns of light and dark, activity and rest. But what happens when these natural rhythms are disrupted? When artificial light extends day into night, when schedules conflict with biology, when the body's ancient wisdom meets modern life's demands? The answers unfold in the delicate dance between your inner clocks and the outside world. The dreamers and the dreamless. Some wander dreamlands nightly, others recall nothing at dawn. What divides them? From genetics to lifestyle, the answers linger in the quiet spaces between neurons. As you surface from sleep each morning, you join one of 2 tribes, those who carry vivid dream fragments into waking life like delicate sea glass gathered from night shores, and those who rise with only the faintest impression that something unremembered has transpired. This fundamental divide in human experience has puzzled scientists and philosophers alike. Why do some remember dreams with cinematic clarity while others inhabit a seemingly dreamless existence? The difference begins in the brain's architecture. Neuroimaging reveals that frequent dream recallers show greater activity in the temporoparietal junction, a region involved in attention and memory encoding, both during sleep and wakefulness. Their medial prefrontal cortex, responsible for self-referential thinking, remains more active during sleep transitions. Essentially, their brains may be wired to better capture fleeting dream imagery before it dissipates like morning mist. Sleep structure itself plays a crucial role. Those who remember more dreams tend to have more frequent nighttime awakenings, however brief, microarousals that create windows for dream recall. They also spend slightly longer in REM sleep, particularly in the final cycles closest to morning. The chemistry of their sleeping brains differs too, with higher levels of acetylcholine, a neurotransmitter crucial for memory, during these dream-rich phases. Lifestyle factors whisper through these neural pathways. Creative individuals often report richer dream recall, possibly because their brains are more practiced at holding on to unconventional imagery. People experiencing emotional distress tend to remember more dreams, particularly unpleasant ones, as heightened amygdala activity makes emotional content more memorable. Even something as simple as bedtime hydration affects recall. Mild dehydration can increase awakenings that facilitate dream memory. The sleep environment itself shapes what we carry into daylight. Waking naturally, without an alarm, allows the brain time to consolidate dream memories. Keeping a dream journal trains the mind to value these nocturnal narratives, creating a self-reinforcing cycle of recall. Sleeping in new locations often increases dream remembrance, likely because the brain remains slightly more alert to potential threats in unfamiliar surroundings. Cultural attitudes create surprising variations. Western societies, with their emphasis on logical waking consciousness, often dismiss dreams as meaningless, a perspective that diminishes recall. The Timur people of Malaysia, by contrast, view dreams as equally real as waking life and consequently report extraordinarily detailed dream memories shared communally each morning. The mystery of dreamless sleepers is particularly fascinating. While everyone dreams during REM sleep, as evidenced by brain scans, some individuals appear incapable of recalling these experiences. Research suggests they may experience fewer micro-awakenings during or immediately after REM phases, those crucial moments when dreams transfer from short-term to long-term memory. Their dreams may also lack strong emotional content narrative structure, making memory. Neurological conditions reveal unexpected dream connections. People with Parkinson's disease often experience vivid dreams preceding motor symptoms, possibly because the disease affects brain regions involved in both movement and REM sleep. Certain antidepressants suppress REM sleep dramatically, yet patients don't report corresponding reductions in dream recall, suggesting dreams may originate from other sleep stages too. The aging process transforms dream recall in complex ways. Children typically remember dreams more vividly than adults, possibly because their longer REM periods and less filtered perception create stronger impressions. Elderly individuals often report decreased dream recall, though this may reflect changes in sleep architecture rather than dreaming itself. With age, we spend less time in the REM phases most associated with memorable dreams. Modern technology offers new ways to capture elusive dreams. Smartphone apps can detect REM sleep through movement and sound cues, then wake users during optimal recall windows. Some experimental devices even claim to detect and record dream imagery by decoding brain activity patterns, though the ethics of such technology remain debated. Yet for all our scientific advances, the fundamental question remains, why does this variability exist at all? Evolutionary biologists propose several theories. Strong dream recall might have helped our ancestors rehearse survival strategies or process emotional events. Conversely, forgetting dreams could prevent confusion between imagined and real events, a cognitive advantage in dangerous environments. As you prepare for sleep tonight, consider your own relationship with dreams. Whether you're a frequent flyer in vivid dreamscapes or a seemingly dreamless sleeper, your brain is still performing its nocturnal alchemy, sorting memories, processing emotions, solving problems beneath conscious awareness. The only difference lies in what traces remain at dawn. But what of those who experience dreams so vivid they blur the line between sleeping and waking? Who find themselves conscious within dreams, able to steer their course like captains of imaginary ships? That extraordinary state of lucid dreaming awaits our next exploration. The Nighttime Alchemists. Melatonin, adenosine, serotonin, these are the chemists in your bloodstream, measuring shadows and stirring drowsiness. Their delicate balances dictate the rise and fall of your rest. As evening descends and daylight fades to twilight, an invisible chemistry begins transforming your body into a vessel for sleep. Within your brain and bloodstream, molecules older than humanity itself begin their ancient dance, measuring the day's length, counting your hours awake, preparing your tissues for renewal. This is the endocrine system's nocturne, a symphony of hormones and neurotransmitters composed over millions of years of evolution, perfectly tuned to Earth's day-night cycle. The performance begins with the light-sensitive cells in your retinas. Unlike the rods and cones responsible for vision, these intrinsically photosensitive retinal ganglion cells, iPRGCs, contain melanopsin, a pigment uniquely responsive to blue wavelengths. As sunlight mellows toward sunset, these cells detect the changing spectrum and send signals along the retinohypothalamic tract to your suprachiasmatic nucleus, SCN, the master clock in your hypothalamus no larger than a grain of rice. Your SCN interprets this dimming light as nature's first cue. It signals the pineal gland, a tiny, pinecone-shaped structure deep in your brain, to begin its alchemical work. Like medieval monks illuminating manuscripts by candlelight, pinealocytes start converting serotonin into melatonin, the hormone of darkness. This transformation follows an exquisite rhythm. Melatonin production typically begins around 9 p.m., peaks between 2 and 4 a.m., then decline as dawn approaches. The chemistry is beautifully simple. Exposure to light inhibits the enzyme that converts serotonin to melatonin, while darkness permits it. But melatonin is only one player in this biochemical ballet. Throughout your waking hours, another substance has been accumulating steadily, adenosine, a byproduct of cellular metabolism. Like sand filling an hourglass, adenosine builds up in your basal forebrain, creating what scientists call sleep pressure. Each hour you're awake, adenosine molecules bind to receptors, slowing neural activity and making you increasingly drowsy. Caffeine works by blocking these receptors, temporarily silencing the chemical whispers urging you to rest. Meanwhile, your hypothalamus adjusts other hormonal balances. It signals the pituitary to reduce production of cortisol, the alertness hormone that peaks at dawn, while increasing GABA, the nervous system's primary inhibitory neurotransmitter. GABA acts like a gentle hand lowering the volume on brain activity, quieting the neural noise that characterizes wakefulness. At the same time, your body temperature begins its gradual descent, a drop of about 1 degree Celsius (1.8 degrees Fahrenheit) that mirrors the planet's nightly cooling. This temperature shift isn't merely a consequence of sleep but an active trigger for it, regulated by the SCN's control over blood flow to your extremities. The gut plays an unexpected role in this chemistry. Enterochromaffin cells in your intestines produce about 90% of your body's serotonin, the precursor to melatonin. This gut-brain axis explains why certain foods can influence sleep quality. Tryptophan-rich foods, like turkey and milk, provide raw material for serotonin production, while complex carbohydrates help tryptophan cross the blood-brain barrier. Your microbiome, the ecosystem of bacteria in your digestive tract, also produces sleep-influencing compounds, including GABA and short-chain fatty acids that affect circadian rhythms. As midnight approaches, the hormonal tides shift further. Growth hormone secretion peaks during slow-wave sleep, facilitating tissue repair and muscle growth. Prolactin, often associated with lactation but present in all adults, increases during sleep, modulating immune function and contributing to sleep's restorative effects. Even your kidneys adjust their filtration rate according to circadian signals, producing less urine at night, a rhythm so ingrained it persists for days in total darkness. The precision of this system is breathtaking. Your SCN maintains its rhythm even when isolated in a petri dish, proving the clock is endogenous rather than purely reactive. Individual neurons in the SCN contain complete circadian oscillators, their electrical activity cycling predictably. These cellular clocks exist throughout your body, in your liver, lungs, and even skin cells, all synchronized by the SCN's master rhythm but capable of independent timekeeping if separated. Modern life has disrupted this ancient chemistry in ways our biology struggles to comprehend. Artificial light, particularly blue wavelengths from screens, tricks the SCN into suppressing melatonin production as if sunset hadn't occurred. Irregular meal times confuse peripheral clocks in your digestive organs. Shift work forces the body into perpetual jet lag, with studies showing night workers have higher risks for diabetes, obesity, and cardiovascular disease, all linked to circadian disruption. The consequences appear in small but telling ways. That midnight snack you barely remember. It signals your pancreas to release insulin on a schedule conflicting with your sleeping brain's expectations. The quick email check at 11 p.m. The burst of blue light resets your melatonin onset like a snoozed alarm. Even weekend sleep-ins create social jet lag, the dissonance between your biological and social clocks that leaves you groggy come Monday. Yet the system demonstrates remarkable resilience. Camping studies show that just 1 week without artificial light resets human circadian rhythms to perfectly match natural dawn and dusk. Strategic. Light exposure, morning sunlight viewing and amber-tinted glasses at night, can dramatically improve sleep quality. Even something as simple as consistent meal times helps synchronize peripheral clocks with your central rhythm. As you lie in bed tonight, consider the invisible chemistry surrounding you. The melatonin in your bloodstream, the adenosine in your synapses, the serotonin in your gut, all collaborating to guide you into rest. These molecules are older than cities, older than agriculture, older than language itself. They are the legacy of countless generations who rose with the sun and slept beneath the stars, their rhythms written into your DNA. But what happens when this ancient chemistry meets modern medicine? When sleeping pills, melatonin supplements, and other interventions attempt to override or augment nature's design? That delicate interplay between biology and technology awaits our next exploration. The borders of consciousness. Sleepwalking, lucid dreams, and hypnagogic whispers live in this twilight realm. Here, the gates between waking and dreaming stand ajar, letting strange visions slip through. As you hover at the edges of sleep, your mind enters a liminal territory where the ordinary rules of consciousness no longer apply. This borderland between waking and sleeping, these fluid transitions where one state bleeds into another, reveal the fragile nature of our perceived reality. The brain does not switch cleanly from wakefulness to sleep like a lamp being turned off, but rather undergoes a gradual, sometimes erratic transition where elements of both states intermingle in fascinating and occasionally unsettling ways. The journey begins with hypnagogia, those fleeting sensory experiences that accompany sleep's onset. As your brain waves slow from waking beta rhythms to the alpha and theta waves of early sleep, you may see swirling colors or geometric patterns behind closed lids. Some hear their name called by an invisible voice, others feel imagine touches or the sensation of falling that jolts them briefly awake. These phenomena represent the thalamus, the brain's sensory gatekeeper, beginning to dampen external input while still allowing internal signals to pass. Artists and inventors have long prized this state. Thomas Edison would nap holding steel balls to wake himself when hypnagogic imagery became most vivid, believing this twilight zone fostered creativity. Further along the continuum lies sleep paralysis, a temporary inability to move occurring either at sleep's onset or upon waking. During REM sleep, your brainstem inhibits motor neurons to prevent dream enactment, but sometimes this paralysis lingers into wakefulness. The experience, often accompanied by vivid hallucinations of intruders or supernatural presences, occurs when the dreaming brain's vivid imagery persists even as you regain consciousness. Cultural interpretations vary widely, from the Newfoundland old hag tradition to Japanese kanashibari, but the neurobiology remains universal, a temporary mismatch between brain regions waking at different speeds. Sleepwalking, somnambulism, represents the inverse phenomenon, the body moving without full conscious awareness. Most common in children during deep non-REM sleep, it occurs when the thalamus fails to fully paralyze the body while other brain regions remain asleep. Sleepwalkers can perform complex actions, eating, dressing, even driving, while their prefrontal cortex, responsible for judgment and self-awareness, remains offline. Far from acting out dreams, which occur in REM sleep with paralysis intact, sleepwalkers are essentially performing automatic behaviors while consciousness sleeps. Lucid dreaming occupies a unique middle ground, the dreamer becomes aware they're dreaming while the dream continues. Brain scans reveal this state combines elements of REM sleep with partial activation of the prefrontal cortex. Experienced lucid dreamers can signal researchers with prearranged eye movements, allowing real-time study of this hybrid consciousness. Buddhist dream yoga practitioners have cultivated this skill for centuries, viewing it as a tool for spiritual growth, a testament to humanity's long fascination with these border states. The spectrum of parasomnias, unusual sleep behaviors, illustrates how easily the boundaries can blur. Exploding head syndrome, hearing loud imaginary noises at sleep onset, sleep-related eating disorder, compulsive eating while asleep, and sexomnia, engaging in sexual behaviors while asleep, all represent different ways the sleeping brain's inhibition systems can misfire. Even common experiences like sleep talking or teeth grinding reveal the nervous system's incomplete transition between states. Children's brains demonstrate these border states with particular clarity. Night terrors, distinct from nightmares, occur when a child becomes agitated during deep non-REM sleep, often screaming inconsolably while remaining asleep. Sleepwalking and confusional arousals, sitting up confused during sleep transitions, reflect immature neural inhibition. These phenomena typically resolve as the brain matures, suggesting such border states may represent temporary imbalances in developing neural circuits. Neurological studies reveal surprising continuities between waking and sleeping consciousness. Patients with damage to the ventromedial prefrontal cortex often report decreased dream recall, linking this region to both waking self-awareness and dream consciousness. The default mode network, active when we daydream, shares remarkable overlap with REM sleep brain activity patterns. Even near-death experiences, with their vivid hallucinations and out-of-body sensations, may represent the brain's attempt to make sense of abnormal neural activity during crisis, not unlike dreaming during physiological stress. Modern technology allows unprecedented study of these borderlands. Hyperscanning EEG can now detect the precise moment when conscious awareness fades at sleep onset. fMRI studies reveal how psychedelic drugs induce dreamlike states by activating similar neural networks. Sleep labs use polysomnography to measure muscle tone, eye movements, and brain waves simultaneously, painting a comprehensive picture of consciousness in transition. Cultural interpretations of these phenomena vary widely. Some indigenous Australian cultures view dreamtime as equally real as waking life. Tibetan Buddhism recognizes 4 states of consciousness: waking, dreaming, deep sleep, and a transcendent fourth state, with practices to navigate between them. Western science traditionally dismissed such states as neural noise, though cognitive neuroscience now validates their significance for understanding consciousness itself. As you prepare for sleep tonight, consider how porous these boundaries truly are. That moment when you're not quite awake nor fully asleep contains mysteries neuroscience is only beginning to unravel. Your brain doesn't simply turn off consciousness like a switch, but rather modulates it along a spectrum, with dreams, daydreams, and altered states representing different points along this continuum. But what happens when we examine sleep not just as an individual phenomenon, but as a shared experience across species? When we trace its evolutionary origins back through millennia of biological development. That story begins in the ancient rhythms of life on Earth. The symphony of circadian rhythms. Your body knows the time without a clock. Light, meals, and even social cues tune this internal orchestra, a rhythm older than cities, older than fire. Before the first human ever carved notches into bone to mark the passing days, biological clocks were already keeping perfect time. These circadian rhythms, the 24-hour cycles governing everything from your body temperature to hormone release, represent one of evolution's most ancient and universal innovations. Woven into the fabric of nearly every life form on Earth. From cyanobacteria to blue whales, this internal timekeeping system orchestrates your physiology with a precision that would make the finest Swiss watchmaker envious. At the heart of this system lies your suprachiasmatic nucleus, SCN, a tiny region of the hypothalamus no larger than a grain of sand. This master clock contains about 20,000 neurons that fire in perfect 24-hour rhythms, even when isolated in a petri dish. The SCN's timekeeping arises from intricate feedback loops in clock genes, like period and cryptochrome, where protein products inhibit their own production before being degraded, creating oscillations as reliable as a pendulum swing. But what makes this system truly remarkable is its distributed intelligence. Nearly every organ and tissue contains peripheral clocks that synchronize with the SCN while maintaining some independence. Your liver knows when to expect meals, your pancreas anticipates dawn before light arrives. Light remains the most powerful zeitgeber, time giver, for your circadian system. Specialized retinal ganglion cells containing melanopsin detect blue wavelengths, sending signals along the retinohypothalamic tract to reset your SCN daily. This light sensitivity follows an exquisite gradient. Dawn's gradual blue light gently halts melatonin production, while sudden artificial light at night can abruptly disrupt it. The system is so precise that blind individuals with intact melanopsin cells maintain normal circadian rhythms, while those without them often develop non-24-hour sleep-wake disorder, their internal clocks drifting endlessly without light cues. Yet light isn't the only conductor of your biological orchestra. Meal timing powerfully influences peripheral clocks in your liver, pancreas, and digestive system. Studies show mice with disrupted feeding schedules develop metabolic disorders even when their SCN remains intact. Temperature fluctuations also serve as cues. Your core body temperature's natural dip at night help initial sleep, while the morning rise promotes alertness. Even social interactions and exercise provide subtle timing signals, though these, weak Zeitgebers, pale compared to light's dominance. The evolutionary advantages of circadian rhythms become clear when examining life across the planet. Flowers open their petals at precise hours to attract pollinators. Monarch butterflies use circadian clocks to navigate their incredible migrations. The humble honeybee's internal timing is so precise it can remember which flowers offer nectar at specific times of day. These biological clocks developed early in evolutionary history. Cyanobacteria, among Earth's oldest organisms, already possess circadian rhythms 2.5 billion years ago, using them to separate nitrogen fixation, oxygen-sensitive, from photosynthesis, oxygen-producing, in time rather than space. Your body's various clocks perform a complex dance throughout the 24-hour cycle. Around 4 a.m., your core temperature reaches its nadir while melatonin peaks. By 6:30 a.m., blood pressure begins its sharpest daily rise. Alertness typically dips in the early afternoon, the circadian siesta zone, before peaking again in early evening. Even your sensitivity to pain follows circadian patterns, with lowest thresholds often occurring during nocturnal hours. These rhythms are so deeply embedded that jet lag occurs not from travel itself, but from your internal clock struggling to realign with new time zones, your liver expecting breakfast while your stomach thinks it's midnight. Modern life has created unprecedented challenges for this ancient timing system. Electric lighting extends daytime into hours when our ancestors knew only darkness. Shift work forces approximately 20% of the workforce to operate contrary to their biological clocks. Even something as simple as weekend sleep-ins can create social jet lag, the dissonance between internal and external timing linked to obesity, mood disorders, and cardiovascular risk. The consequences appear in both subtle and dramatic ways. Hospital errors peak during night shifts, students perform worse on early morning exams, and heart attacks occur most frequently around 9 a.m. when blood pressure surges meet increased platelet stickiness. Yet emerging research reveals promising strategies for circadian alignment. Light therapy boxes can help reset rhythms for shift workers or those with delayed sleep phase disorder. Strategic meal timing, even without dietary changes, has been shown to improve metabolic health. The study of circadian rhythms extends far beyond sleep. Your immune system's effectiveness fluctuates predictably throughout the day. Vaccination responses improve when administered in the morning. Cancer cells may exploit circadian disruptions to promote growth. Astronauts experience circadian misalignment from 90-minute days in orbit, prompting NASA to develop lighting systems that mimic Earth's cycles. Even the timing of medical procedures, from surgeries to chemotherapy, shows circadian influences on outcomes. As you move through your day, consider the invisible rhythms guiding your every function. That afternoon energy dip isn't laziness, it's your circadian system preparing for a second wind. The difficulty falling asleep after late-night screen time reflects millions of years of evolution expecting darkness after sunset. Your body doesn't merely respond to time, it anticipates it, preparing your liver for food before you feel hungry, raising cortisol before dawn to ease your awakening. But what happens when we zoom out from individual biology to the grand scale of life on Earth? When we consider how every creature, from single-celled organisms to giant sequoias, dances to these same ancient rhythms. That panoramic view reveals sleep as nature's most universal language. Good night.